Welcome everybody to our business math course. We are going to discuss definite integrals, the fundamental theorem of calculus. This is Magda Talib Al-Hinai from Sultan Qaboos University. We start our discussion considering the function whose curve is in front of us on the xy plane. This is f of x, and we take f of x to be continuous over the closed interval ab. We have ab in front of us on the curve. Let me grab my laser pointer so that I continue using it. Here's the ab interval, and the f of x is continuous on this interval. Also, we put another assumption that the curve of f of x is always lying above the x-axis, and this is an assumption we take for the time being, and then we will generalize it. So we mean by the curve lying above the x-axis that f of x is greater than or equal to 0. Now we consider the area function, which is a of x, and we define a of x to be the area bounded by the curve f of x, bounded by the curve f of x and the x-axis from a to the point x somewhere in between a and b. So we see it in front of us. Here is a of x starting from a to x. And now we mean by a of x this shaded area. Of course, if x gets closer and closer to a, the area is getting smaller and smaller until the value x equals a. Here, the area will be equal to 0. A of a is equal to 0. And if I go further till the point b, we know that the area is equal to the integral from a to b of the function f of x. So a of b is equal to the integral from a to b f of x dx. Now we have the antiderivative function of this function f of x. We always call it capital F of x. So if I consider the area to be the integral of the function f of x from a to x, we can get this result that a of x is the antiderivative plus the constant of integration. In order to find the constant of integration, we take this into account and we plug here a, so we get a 0, and accordingly c will be equal to minus f of a. And hence, I take this minus f of a and I substitute in this equation. We get a of x is equal to f of x minus f of a. Okay, if I take x equals to b and I plug it in this equation for each value, for each x, I put the value b. So I get a of b equals f of b minus f of a here. But from this equation and this one here, we can rewrite this formula, replacing a of b with this integral. So from 1 and 2, we have the integral from a to b of f of x dx is equal to f of b minus f of a. And of course, this is capital F. And in the general case, when we have f of x is any continuous function on the interval from a to b, not necessarily only the ones which are greater than or equal to 0, for any f of x which is continuous on the closed interval ab, if we have this, and we call it the fundamental theorem of calculus. In this slide, I'm going to put in front of you the fundamental theorem of calculus, and I will start with a continuous function f. I have here the function f is in the lower case, which is continuous on a closed interval ab. And this f has an antiderivative capital F. Capital F is the antiderivative of f on ab. Then the integral from a to b of f of x dx is equal to the antiderivative of this function, which is capital F, evaluated at b minus capital F evaluated at a. And here it's very important that we know the difference between the definite integral, where we have two values here, one below and one up, and the indefinite integral where we have no values, we're just integrating f of x dx. The definite integral is giving you a number, a value, while the indefinite integral is giving you a function f of x, as capital of X is giving you the antiderivative function, which when differentiated, you get this function. Okay, let's see some properties of the definite integral. And suppose we have f of x to be continuous and non-negative on the closed interval ab, then the definite integral of f of x from a to b represents the area bounded by the curve of f of x and the x-axis, as well as the two vertical lines x equals a and x equals b. And let me grab my laser pointer again to come and explain on a graph here. So here we have the function f of x, and this is the x-axis. Here is the vertical line x equals a, and this is also the vertical line x equals b. So this area, which is bounded by the four things, the curve, the two vertical lines, and the x-axis, is given by this definite integral. This was the first property. The second property, we call it the linearity property, where we have the functions f of x and g of x being multiplied by two constants alpha and beta, and we have the sum of difference between these two functions, alpha f of x, beta g of x, and we integrate it from a to b. Then this is equal to the integral of the first, where we take the constant outside the integration sign, plus or minus the integral of the second, where also we take the constant of the constant here, which is multiplied by the function g of x outside the integral sign. The third property, if we integrate from a to a, then definitely this is equal to 0, and we mentioned this earlier. Also, the integral from a to b of the function f of x dx is minus the integral from b to a of f of x dx. These are two properties. And finally, we come to the last property, where we have the integral from a to b can be split into two parts, from a to c and then from c to b, where c is a point belonging to the closed interval a b. Here comes our first example. We want to evaluate the definite integral x power 4 plus 4x plus 4 dx from 1 to 4. We start our solution putting the whole integral equal to I. So, and we go ahead and integrate term by term, applying the linearity property of the definite integral. So we have I equals the first term, the integration of the first term, yes, plus the integral of the second term, yes, and we took the 4 outside, plus the integral of the third term, and also we took the 4 outside, and we colored the ones in red and the 4s in green, and we continue our solution. We do the coloring only for the sake of illustration. So what's the integral of x power 4? It's x power 5 over 5. What's the integral of x dx? It's x squared over 2, and here comes the 4. What's the integral of dx? It is x, and here also comes the 4, and all this will be evaluated from 1 to 4. So the next step, we evaluate this thing at x equals 4, and then we evaluate it at x equals 1, and we find the difference. So, but first let us cancel the 4 and the 2 together. So we have this for the substitution of each x to be 4, minus, again, we substitute for each x to be 1. Evaluating this bracket and this bracket, we arrive at the numerical value 246.6. Let's see this example, but first let me grab my laser pointer, and we want to integrate or evaluate the definite integral of 5x squared e power x cubed dx from 0 to 2. We start our solution calling this thing I. And we need to make a substitution for x cubed to be t. So let's do this substitution. Put x cubed equals to t. Accordingly, we need to find a relation between dx and dt. We differentiate both sides, so we get the differentials dx and dt in one equation. This equation is equivalent to saying that x squared dx is dt over 3. So whenever you see the x squared dx, you put instead of it dt over 3. It's not only this. We know that x varies from 0 to 2. What about t? So we need to find the limits of the new variable. For the old variable, we had that when x equals 0, what is t? We should try to find that the lower limit is 0 in the case of x. What is it in the case of t? It's also 0 because 0 cubed is 0. What about the upper limit? Let's see. At x equals 2, this 2, we take the 2 and cube it, so we get t equals to 8. Now we make substitutions of everything we found here. The x cubed equals to t, the x squared dx equals to dt over 3, and also the limits from 0 to 8 for the new variable. So we take x cubed equals t, we take x squared dx is equal to dt over 3, and we substitute in this equation. So we arrive at this integral. Yes. So again, this is the I, yes. So the lower limit is 0 and the upper limit is 8. What's the integral of e power t? It's e power t over 1. So this is e power t, and the 5 over 3 is here also. So we put our lower limit 0, our upper limit is 8, and then we apply the fundamental theorem of calculus where we have e power 8 minus e power 0 as follows. So this is equal to 5 over 3 e power 8 minus e power 0, which is 5 over 3 e power 8 minus. Now let's see another example. Evaluate the definite integral of f of x from 0 to 2, where f of x is defined by the piecewise function we see in front of us on two domains from 0 to half. F of x is equal to 4x squared, and on the closed interval from half to 2, f of x is equal to 2x. So we start our solution by splitting the function, the integral of the function from 0 to 2 into two integrals. The sum of two integrals from 0 to half, and then the other integral from half to 2. So we integrate f of x from 0 to half because on this domain f of x has a definition, and then we integrate it from half to 2 because again on this domain f of x has another definition. See, the half is belonging to the interval from 0 to 2, so we can do this splitting. Now, on the semi-closed interval from 0 to half, what's the definition of f of x? It is 4x squared. So we write the integral as follows. And we do the same thing for the other integral. On the interval from half to 2, we have f of x equals to 2x. Yes. So now we go ahead and integrate as we do as usual. So what's the integral of 4x squared? It is 4x cubed over 3. And here we have the limits of the integration. Plus, what's the integral of 2x? It is 2x squared, and the 2 cancels with the half. So we have x squared is the value of the integral, and the limits of integration are half and 2. So we substitute in the first part by the upper and the lower limits, and we get this. Plus, again, we substitute in this part by the upper and the lower limits to get this. And making simplifications, we arrive at 1 over 6 plus 4 minus 1 over 4. Making common denominator, we arrive at 47 over 12, which is equal to 3 and 11 over 12. Let's see this example. We are given the definite integral of f of x from 1 to 2 to be equal to 5, and the definite integral of f of x from 3 to 1 to be equal to 2, and we are asked to find the value of the definite integral of f of x from 2 to 3. First of all, let's look at this integral. It is from 3 to 1. Why don't we put the smaller down and the bigger limit up? So let's see how can we do this. In the solution, we start with the integral from 1 to 3 of f of x dx is equal to minus the integral from 3 to 1 of f of x dx. This is one of the properties we've taken for the definite integral. Accordingly, this integral is equal to minus 2. Let's call this equation 1. On the other hand, we can write this integral from 1 to 3 of f of x as the sum of two integrals, the definite integral of f of x from 1 to 2 plus the definite integral of f of x from 2 to 3. And we call this equation 2. So let's have a look at this definite integral. We have its value here. It is 5. Also, from equation 1, we can replace this by minus 2. So let's see what can we write next. Yes, minus 2 here and the 5 here, plus the integral we are looking for its value, which is the definite integral of f of x from 2 to 3. Simply, we can say that this is equal to minus 7. Finally, we come to our last example in this presentation, where we are going to solve a word problem. We have the marginal cost function to be given in the form dc by dq is equal to 3 over 5q plus 2, where q is the quantity of units produced, as we know. And we are given that the production is set at, initially set at 80 units per week, and we are asked to find how much more will it cost to increase production to 100 units per week. In order to start solving this problem, we need to tell you that the definite integral of a derivative is given by the formula in front of us. Suppose I have f prime of x and I want to integrate it from a to b over x. So this is equal to f of x evaluated at b minus f of x evaluated at a. Accordingly, in our case, we will have the definite integral of the marginal cost from 80 to 100 is equal to the cost of producing 100 units minus the cost of producing 80 units. Actually, this gives us the change in cost as the production increases from 80 to 100 units, which is exactly what we are asked to evaluate. So we start integrating. We take the dc by dq and we substitute for it by 3 over 5q plus 2, and we perform integration term by term. The integral of the first term, here the q will be q squared over 2, and here we will have 2q. So this will give us 3 over 10 q squared plus 2q. And then we evaluate this at 100 and evaluate it again at 80 and find the difference between them. So here we have 3 over 10 q, we put 100. So here we have 100 squared plus 2 times 100 minus 3 over 10, 80 squared plus 2 times 80, where I leave the rest for you